Hi everyone. We will now continue with our discussion on the frequency response of single stage MOS amplifiers. In the previous lecture, we discussed about the frequency response of common source amplifiers and we saw the impact of different parasitic capacitances on the frequency response. Now we will do we'll perform a similar analysis on common gate amplifiers as well and show the effect of different parasitic capacitors on the performance of common gate amplifiers. Now just to quickly look at the different sources of parasitic capacitors, you will have one source to bulk capacitance here, drain to bulk capacitance to ground, and one gate to source capacitance and a gate to drain capacitance. So we'll have total 4 capacitors, but luckily they could be just lumped into an input capacitance and an output capacitance. So C1 here can be written as CGS plus CSB and C2 here can be written as CDB plus CGD. You can also have some load component CL. Now this makes the analysis of a common gate amplifier much simpler. But you have to keep in mind, when does one use a common gate amplifier? What are the important properties of a common gate amplifier that are of interest to us? We said the input impedance of a common gate amplifier is very less. Common gate amplifiers can be used as voltage amplifiers only in cases when your source resistance is 0. If your source resistance is very small, it can give you very good amplification. And we said in specific cases, it does still find its applications in radio frequency circuits where the input impedance need not be very high. The input impedance usually is matched to some few tens of ohms. In such cases, common gate amplifiers find its applications. So keeping this in mind, we will analyze common gate amplifiers and look at all the important parameters of it and how they change as a function of frequency. So first I'll do a brute force analysis of a common gate amplifier. I'll start with the circuit and analyze and find all the poles and zeros. To analyze the circuit, I'll first find this node voltage Vx, and then we can analyze this half of the circuit separately. So I've written the circuit, split the circuit into two halves. So by looking into the source terminal of a common gate amplifier, the input impedance is 1 by Gm. Here I'm assuming R0 is infinity. We'll see how it changes towards the end of the lecture when we consider R0. But right now I'm assuming R0 as infinity, so the looking in impedance is just 1 by Gm. So the circuit at the input port can be reduced to something like this. It's a simple RC circuit. And then we have the other part of the circuit, which is a MOS device and a resistor and capacitor in parallel to the load terminal. Now we will do a quick analysis of this circuit. So find the DC gain, and this circuit has 0 at omega equal to infinity because that is the only value of S when this impedance goes to 0. And I also discussed something called short circuit time constants, especially if you have a single capacitor. The system will have one pole. All you need to do is short circuit the input and find the total resistance seen by the capacitance. The total resistance seen by the capacitance, then 1 by C into R equivalent will give me the pole location. Okay, so this is valid for first order systems. If you have just one capacitor, you can apply this. Find the total resistance seen by the capacitance, then 1 by the capacitance here, in this case C1 times R equivalent, will give us the pole. If all the resistors are positive resistors, then we will get a left of plane pole. So using that, I can directly calculate the pole for this system as 1 by C1 into the equivalent resistance is Rs in parallel with 1 by Gm. So you get the pole as 1 by 1 plus S into C1 into Rs parallel 1 by Gm. Then the DC gain of the system is measured when C1 is open circuited, so the impedance of the capacitance is infinity. At that point you get 1 by Gm by Rs plus 1 by Gm, so it gives us 1 by 1 plus Gm Rs. Now at the output port, you can analyze the circuit in a similar way. If you apply an input signal Vx here, you will have a current GM Vx flowing from source to drain. because this is Vx is minus Vgs here. So this current flows into an impedance of value RLC2. So by now we know if you have an impedance which comprises of a resistor and capacitor in parallel, we know how to analyze it now. The impedance is given by RL by 1 plus SC2 RL multiplied by the current, you get Gm times Vx. This is the transfer function from V0 to Vx. So the overall transfer function is given by GMRL by 1 plus GMRS. So if you notice this is nothing but the DC gain of your common gate amplifier. Because of the finite source resistance, your gain is decreasing by a factor of 1 plus GMRS. Just to quickly compare it with a common source amplifier, we said even though we had a source resistance in case of a common source amplifier, the DC gain was independent of RS. It was always minus GMRL. But in case of a common gate amplifier, the DC gain reduces by a factor of 1 plus GMRS because of its low input impedance. Which is why if your source resistance is very high, common gate amplifier is not a good candidate for voltage amplification. Now the overall transfer function includes both the poles here, which is 1 plus SC2RL into 1 plus SC1 into RS parallel 1 by Gm. Now here I am going to make some approximations and see how the frequency response looks before and after adding the parasitic capacitors. I am going to assume that there was a large load capacitance at the output, CL, which is much greater than the parasitic capacitors. So previously, let's assume there was only one capacitor RL, CL, and there was no parasitic capacitors. So which means C1 is purely parasitic, which is CGS plus CGD, CGS plus CSB, so that is 0. So this pole doesn't exist. So you'll have only one pole, which is 1 by 1 plus S CLRL. So that's what I've shown on the pink curve. The pole is 1 by CLRL. Now, when you include both the poles, DC gain is the same. It is independent of the parasitic capacitors. Now, when you include both the poles, you should look at the pole values here. If I assume GMRS to be much greater than 1, GMRS to be much greater than 1, then I can approximate the second pole 1 by CL C1 into RS parallel 1 by GM as approximately GM by C1. And I can assume this to be at a much higher frequency because 1 by GM is a very low impedance. So the pole is generally given by the capacitance times the impedance seen there. If the impedance value is less, then the pole will be at a higher frequency. So we can say the dominant pole, I introduced what dominant pole is in the previous lecture. When we have multiple poles in a system, the lowest frequency pole will dictate the overall behavior of the system. So that pole we call it as the dominant pole. The dominant pole remains more or less the same, which is 1 by CLRL. I have assumed CL to be much greater. So C2 here is CL plus CDB plus CGD. I have assumed it to be much greater than the parasitics. So that's going to be the dominant pole. So here if you see, there is a second pole, but that occurs at a much higher frequency. Okay, the reason why it occurs at a much higher frequency is because the impedance is very small. You have a capacitance which is just a parasitic capacitance, but it's getting multiplied by a very low impedance, which is 1 by Gm. So therefore, that pole will be at a much higher frequency. So unlike a common source amplifier, where its frequency response was significantly degraded because of CGD, you don't see that problem here. That's because there is no Miller effect. There is no capacitance between two high gain points. So that's why the frequency response is not as degraded when you include all the parasitic capacitors. But you should keep in mind, common gate amplifiers by themselves are not used often in voltage amplification. They are used only if the source resistance is very small. And because of their very low input impedance, they are very commonly used as current to voltage converters or current amplifiers or current buffers. So here I have shown the frequency response graph assuming the source resistance is 0. If RS is 0, there is no second pole. So and the DC gain also increases, it becomes 20 log GMRL. So GMRL is your DC gain of a common source amplifier, common gate amplifier with RS equal to 0. Gain is very high and the pole will be at 1 by RLCL. So if your RS is 0, you don't need time to charge these capacitances. So therefore there is no time constant associated at the input port. So you will not see any poles at the input port. So that's it about common gate amplifier. So we analyzed common gate with and without source resistance, and we said some things about common gate amplifiers, that they are generally used as current buffers, or they are always used in conjunction with common source amplifier, so which is cascade amplifier, or sometimes with common drain amplifier. Because if you want to use them as voltage amplifiers, they need to have very high input impedance. Common source and common drain have very high input impedance, which is why they are very commonly used for voltage amplification or buffering. A common gate amplifier, on the other hand, it is normally used in conjunction with a common source amplifier or as a current buffer. So since we said it is often used as a current buffer, a very important property of a common gate amplifier is its input impedance. Its input impedance is supposed to be as low as possible, because if it is used as a current buffer or a current amplifier, it needs to have a very low input impedance. We will now see how does this input impedance change as a function of frequency. Now, since I am measuring at the input node, I am going to ignore the capacitors. Capacitors are anyways going to come in parallel at the input. I will see the effect of this input impedance due to the load capacitance. What happens to the input impedance due to a load capacitance and a load resistance? Now, before we analyze the circuit rigorously, we can quickly perform an intuitive analysis and see what happens under limiting or boundary conditions. So first, at DC, the input impedance at DC is when the capacitance is an open circuit. You are looking into the source terminal. Now here there are two conditions. If R0 is infinity, so if R0 is infinity, then it really doesn't matter what you connect at the drain terminal. The input impedance is always going to be equal to 1 by Gm. It will never change, it will always be 1 by Gm. But in practice, you will have always a finite R0, and especially in small channel devices, R0 can be significant. Okay, small channeling devices, R0 can be significant. When it is significant, it can be lower. So in that case, you will have to consider R0. So considering R0, again I am going to quickly perform an intuitive analysis and show that if you look at this circuit here, at DC, the input impedance, even if R0 is present, at DC, input impedance is going to be a very strong function of the load impedance, RL. I'll introduce a result, I'll come to that, but I'll just leave it aside that it's going to depend on the load resistance RL. At very high frequencies, I'll very briefly come to what is this value of ZA of 0. I'm just saying that it can be some value. Now because of RL, it will have a strong dependence on RL as well, the input impedance. Now at infinite frequencies, the capacitance will act like a short circuit. If the capacitance acts like a short circuit, the circuit reduces to something like this. Drain is at AC ground. So when you look into the source terminal, the input impedance at infinite frequency will be 1 by Gm parallel R0, which will be R0 by 1 plus Gm R0, or approximately 1 by Gm itself. Now I'll use an equation which I had already derived for common gate amplifiers previously. That is, if I have a load impedance, at the drain terminal, then the looking in impedance in a common gate amplifier is given by, so in the presence of R0, if R0 is infinity, it is just 1 by Gm, but otherwise it's given by R0 plus ZL of S divided by 1 plus Gm R0. So the impedance here gets divided by the gain of this amplifier, the reverse gain of a common gate, the reverse intrinsic gain of a common gate, which is 1 plus Gm R0. So you get R0 by 1 plus Gm R0 plus ZL of S by 1 plus Gm R0. Now I have an input exact expression for the input impedance. I want to find poles and zeros for this expression. So I have two resistors, so I have two impedances in series. So I have one R naught by 1 plus GM R naught plus ZL of S by 1 plus GM R naught. Now it's very easy to find pole. I just need to find, this term is constant, it doesn't depend on S, but this term depends on S. All I need to find is condition when this impedance blows up to infinity. So when the impedance ZL of S blows up to infinity, that will be your pole. And since ZL of S is just a parallel RC circuit, it's just RL and CL in parallel, the point where it will blow up at infinity will be S equal to minus 1 by RLCL, or omega P is 1 by RLCL. So that's the location of pole. Now to find 0, I'll just equate the numerator here to 0. So if ZL of S becomes equal to minus R naught, I get the condition for 0. So solving that, ZL of S equals to minus R naught, I'll get the 0 location as minus of 1 by CL into R naught parallel RL. So you can equate ZL of S, or you can equate minus 1 by R naught as YL of S, the admittance of the output. So admittance is given by 1 by RL plus SCL. So by solving this, you can directly show the 0 will be at minus of 1 by CL into R naught parallel RL, or this is a left of plane 0. So now we know 0 and pole for the system, and we can try to plot the frequency response. Before we plot the frequency response, we should see that since the input resistance with a finite load resistance will be 1 by GM plus some value plus RL by 1 plus GM or not, this I can say is always going to be greater than 1 by GM. So the value at DC, which is when the capacitance is open circuit, the input impedance will be 1 by GM parallel R naught, I have ignored R naught now, plus RL by 1 plus GM R naught. This is definitely greater than 1 by GM. At very high frequencies, when the capacitance completely shorts out the drain terminal, you will have an impedance of just 1 by GM parallel R naught, or which is equal to 1 by GM itself, approximately equal to 1 by GM itself. So that's what I have shown in this graph. You start from this value, which is 1 by GM plus RL by 1 plus GM R naught, and eventually you reach 1 by GM. So it goes from a higher value to a lower value. Impedance decreases as a function of frequency, which means you should first encounter a pole and 0 next. If I want to go from a higher value to a lower constant value in a Bode plot, you will have to first encounter a pole and then a 0. If you encounter 0 first, then it will increase. So we can't have that. So you have to encounter pole first. Now here you can see the 0 location is given by 1 by CL into R naught, CL into RL into R naught by RL plus R naught. I can also express this term as 1 by CL RL into 1 plus RL by R naught. And the pole is simply equal to 1 by RL CL. So we can see 0 is higher by the pole by a factor of 1 plus RL by R naught. So that's what this expression tells us. This expression tells us that the frequency response graph shows us the input impedance decreases as a function of frequency. The next step is to find the output impedance of a common gate amplifier. Again, when we are finding both the input and output impedances, I am considering R naught. Okay, I am considering R naught when we are including output resistances. So here, to find the output resistance, this is the result we have already derived. This is nothing but a source degenerated amplifier. I am looking at the drain terminal. So if let Zs of S be the source impedance, then the output impedance looking at the drain terminal is simply given by R naught plus this impedance Zs of S multiplied by 1 plus GM R naught. The opposite happens in case of output impedance. If you saw the previous case, the input impedance was getting, the load impedance was getting divided by 1 plus GM R naught. Here it's getting multiplied by 1 plus GM R naught. So output impedance will be R naught plus Zs of S into 1 plus GM R naught. Now we will first estimate poles and zeros intuitively, and then we will try to find it using expression as well. So if you look at this circuit, intuitively if you want to find poles and zeros, we should first be able to find the impedance at the limiting or boundary conditions. At DC, the capacitance is open, so it will be just a cascode output impedance, so which will be R0 into GMRS, or we can also write the exact expression. It will be R0 plus RS plus GM RS, which is a very high value. We need this to be a very high value, so it's a very high value. At infinite frequencies, this capacitance CS will act like a short circuit. So therefore, the output impedance when you look into the drain terminal will just be R0 itself. So eventually it comes to R0. So we can intuitively see that you'll have to first encounter a pole and then a zero. You have to encounter, the system will have one pole, one zero. So we'll have to now find what is that pole and zero. So we have the expression for impedance here. Pole can be readily found by finding the value of S for which Zs of S blows up to infinity. If this term blows up to infinity, the overall impedance will also be infinity. So we'll have to just equate Zs of S to infinity and find that condition. Zs of S is simply a resistor and capacitor in parallel. So the pole frequency will be 1 by RSCS. Okay. So that's the condition where the transfer function blows up to, the impedance blows up to infinity. The next condition is to find the zero. For that I can just equate this term to 0. If I equate this term to 0, I get Zs of S equal to minus of R0 by 1 plus Gm R0. This R0 by 1 plus Gm R0 is nothing but R0 in parallel with 1 by Gm. This I can approximate it to 1 by Gm. Zs of S equals 1 by Gm. That reduces to, by using this condition, Zs of S is nothing but Rs in parallel with 1 by SCS. You can directly solve and get the pole as minus of 1 by CS into Rs parallel 1 by Gm. Again, I'll make this approximation. GMRS is much greater than 1. Using that, I'll directly get the pole as the 0 as minus of Gm by CS. This is a left of plane 0. So if I write it in radians per second, it will be just Gm by CS. So now we have the transfer function. This is the DC output resistance, which is R0 plus RS plus Gm R0 RS. And you have a pole at 1 by SCS RS and a 0 at 1 plus SCS by Gm. This is an approximate value. So we can see this intuitively also. If your Zs blows up to infinity at some value, then the output impedance will also be infinity, because your source impedance is infinity, output impedance will also be infinity. So that the pole here makes proper sense. So this is what this is the frequency response of output impedance of a common gate amplifier. The common gate amplifier, we want as high an output impedance as possible, because if you're going to use it as a current source, a current amplifier, it needs to have a very high output impedance. And that output impedance will decrease significantly as frequency increases. So first you will encounter a pole which is at minus 1 by RSCS, then a 0 at Gm by CS. So again, if you recall, I have derived this result assuming GMRS to be much greater than 1. So which means 1 by RS is much less than Gm. So that's why you can see this term here, this is 1 by RS into CS, this is Gm by CS. So this term is much smaller. So that finishes our discussion on common gate amplifier, the frequency response of common gate amplifiers. What we saw here, the take home points is that the common gate amplifier's frequency response remains more or less the same. If you assume output capacitance to be the dominant capacitance, a really large capacitance compared to the parasitics, then the frequency response graph remains more or less the same. The reason is the pole at the input port occurs at sees a very low input impedance. The capacitance at the input port sees a very low impedance, therefore the pole is at a much higher frequency. The second thing, we saw how the input impedance changes as a function of frequency, and we also saw how the output impedance changes as a function of frequency. And we mentioned the usual points that common gate amplifier is typically more preferred to be used as a current amplifier or a current buffer. As voltage amplifier, it will still find applications provided you're driving it with a very low source resistance, it will find its applications. Okay, so I'll stop at this point. We'll move on to common drain amplifiers in the next lecture.